You think cold is simple, you imagine it as just less heat, less energy, less movement. Just turn the temperature down and everything slows quietly to a stop. You picture space as empty darkness, frozen, dead, finished. You are wrong. Cold is not the absence of something. Cold is behavior. Cold is structure. Cold is rules you never learned. You think the coldest place in the universe is far away from everything. Far from stars, far from light, far from energy. You imagine distance creates cold. It doesn't. Not in the way you think. There are places in space where temperature stops behaving like temperature. Places where matter forgets how to act like matter. Places where nothing is still doing something, and NASA didn't just measure cold. They found environments where your everyday intuition about reality collapses. Quietly, completely, not violently, not dramatically, just incorrectly. The problem is not that space is colder than you imagined. The problem is that cold itself is not what you think it is. And if that is true, then your picture of reality is built on a misunderstanding. You were taught to think of temperature like a volume knob. Turn it down and energy disappears. Turn it far enough and everything should stop. Molecules freeze. Motion ends, reality goes quiet. This is wrong. Temperature is not a measure of how much energy exists. It is a measure of how energy is shared, how it moves, how it fluctuates between particles. Temperature is behavior, not inventory. You imagine heat as something stored inside matter like water, inside a container. You imagine cold as draining that container. Less heat inside means colder. Empty container means absolute zero. But particles don't store heat the way you store water. They exchange energy constantly. They collide, they vibrate, they interact with radiation. They exist in probability clouds, not fixed positions. Even when energy is low, behavior does not simply stop. It changes character. Imagine a crowded room where everyone is talking loudly. That feels like heat. Now imagine the same room where people whisper. That feels like cold, but the room is still full of people. Conversations still exist. Information still moves. The activity has changed form, not disappeared. At extremely low temperatures, particles do not just slow down like cars running out of fuel. They begin to synchronize. Randomness fades. Collective behavior emerges. Instead of many independent motions, you start seeing shared motion. Pattern replaces chaos. Your intuition says colder means simpler. Physics says colder often means stranger. Because temperature is statistical. It describes averages across huge numbers of particles. But when energy becomes extremely low, averages stop telling the full story. Quantum effects stop being hidden by randomness. They become dominant. You expect stillness. Instead, you get coherence. At room temperature, atoms behave like strangers in a city. They collide, scatter, exchange energy randomly. At extremely low temperatures, they can begin to behave like a choir. Many voices, one note. Many particles, one shared quantum state. This is not intuitive, because your brain evolved to understand warm environments, where randomness dominates and individual behavior matters more than collective quantum effects. Even the idea of motion stopping is misleading. Absolute stillness would require knowing both position and momentum perfectly. Physics does not allow that. Even in the lowest energy state possible, uncertainty remains, fluctuation remains, not because of measurement errors, because reality itself is built that way. So, when you imagine cold as the slow fade into nothingness, you are projecting everyday experience onto a universe that does not follow everyday rules. Cold is not death of motion. Cold is transformation of motion. Cold is where individuality begins to dissolve. And NASA did not just measure low temperatures. They entered regimes where matter behaves less like objects and more like shared possibilities. The deeper you go into cold, the less reality behaves like solid things sitting in space. The more it behaves like patterns that happen to look like things when energy is high enough. This is why the coldest experiments ever performed do not look like frozen blocks of matter. They look like matter losing its boundaries, losing its separateness, losing the very features your intuition expects matter to have. And this is only the beginning of the problem. Because once you stop thinking of cold as nothing happening, you are forced to ask a harder question. If cold is not absence, then what is it really measuring? You imagine space as a giant freezer, endless darkness, no sunlight, no warmth, just silent, permanent cold pressing in from all directions. This is wrong. Space is not cold in the way air is cold, because space is not a thing. It is not a substance surrounding you, pulling heat away from your body. It cannot touch you, it cannot conduct heat, it cannot feel cold. On Earth, when you feel cold, you are feeling energy leaving your body through contact. Air molecules hit your skin and carry energy away. Wind increases collisions. Water pulls heat away even faster. Cold is interaction. Space has almost none of that. If you were floating far from any star, you would not instantly freeze solid. You would lose heat slowly, mainly by radiation. You would glow your energy away as infrared light. That process is real, but it is not violent, not fast, not dramatic. Your body would still be warmer than the surrounding universe for a long time, because temperature only exists when energy can be exchanged. This is the part your intuition rejects. You think temperature is something an environment has, but temperature is something systems share through interaction. Without interaction, temperature becomes a strange, incomplete idea. An isolated object in deep space does not instantly become the temperature of space. It slowly drifts toward equilibrium with the background radiation of the universe. That background is extremely cold. But the path toward it is slow, quiet, patient. Space is not sucking heat out of things. There is nothing there to suck. Instead, objects radiate energy away, because they are warmer than the surrounding radiation field. They glow. Everything above absolute zero glows. You glow right now. You just glow in wavelengths your eyes cannot see. In deep space with nothing nearby, radiation becomes the only conversation matter can have with the universe. And that conversation is slow. This creates a strange situation. Two objects floating near each other in space might exchange heat with each other faster than they exchange heat with the universe around them. Local interaction matters more than cosmic emptiness. Even stranger, direct sunlight in space can be brutally hot. Astronauts in orbit experience extreme heating in sunlight and extreme cooling in shadow. Not because space changes temperature, but because radiation input changes. This destroys another intuition, that temperature is a property of location. In space, temperature is a property of exposure. Exposure to stars, exposure to background radiation, exposure to nearby matter. If you place an object in sunlight in space, it can heat to temperatures hotter than boiling water. Move it into shadow, and it will slowly cool toward the cosmic background temperature. Same location, same vacuum, completely different thermal behavior. Vacuum is not cold, vacuum is neutral. This matters because when NASA searches for the coldest regions of space, They are not just looking for empty places. They are looking for places where radiation exchange is minimized, where structure blocks energy, where expansion spreads energy thinner and thinner. The coldest parts of the universe are not simply far away. They are thermally isolated in very specific ways. This is uncomfortable for your intuition, because it removes the idea that the universe has natural temperature zones like climate regions on Earth. Instead, the universe is a network of energy exchanges. Where those exchanges are weak, cold emerges. Not as a substance, not as a force, but as a pattern of limited interaction. And once you accept that space itself is not cold, another question becomes unavoidable. If emptiness does not guarantee extreme cold, then where does the deepest cold in the universe actually come from? You imagine the coldest place in the universe as the deepest possible void, the farthest point from every star, the darkest pocket between galaxies, the most abandoned region reality can produce. Distance, you think, must equal cold. This is wrong. The universe has a baseline temperature, not because space contains heat, but because the universe itself is filled with leftover radiation from its beginning, a faint glow that exists everywhere, in every direction, at all times. This is the cosmic microwave background, and it sets a floor, a universal thermal whisper that never fully disappears. Right now, that background temperature is about 2.7 Kelvin above absolute zero. Almost unimaginably cold, but not zero, never zero. This means that most of the universe is quietly bathed in this ancient radiation. Even in deep voids between galaxies, this faint glow still touches everything. It is weak, but it is everywhere. So, the coldest natural places cannot simply be empty space, because empty space is still filled with this background radiation. To get colder than that, something strange must happen. Something must push energy away faster than the universe replaces it. This is where your intuition begins to break down again, because one of the coldest known natural regions ever discovered was not deep in an empty void. It was created by structure, by matter, by activity. It was a giant cloud of gas expanding outward extremely fast inside a dying star system. As the gas expanded, energy spread thinner and thinner. The particles inside moved farther apart. Collisions dropped. Radiation interactions weakened. Temperature fell below the cosmic background. For a moment in cosmic time, that expanding cloud became colder than the natural thermal baseline of the universe. Colder than most empty space. This sounds backwards. Activity creating cold, expansion creating cold, motion creating cold. But temperature is not about motion alone. It is about random motion. When expansion stretches energy across a larger volume, random motion can decrease. Structure can drain thermal behavior. This is similar to what happens when gas expands in certain cooling systems on Earth. But in space, with massive scales and near-perfect isolation, the effect can become extreme. The key idea here is subtle but important. The universe does not enforce temperature from the outside. Temperature emerges from how energy is distributed locally. You expect the universe to have a thermal hierarchy. Hot near stars, cold far away, colder farther away, but the real picture is more chaotic. Local physics can override cosmic averages. There are pockets where expansion cools matter faster than radiation warms it. Regions where energy density drops faster than energy can flow back in. These become temporary islands of extreme cold. And because the universe is expanding overall, there is a deeper consequence. On the largest scales, average energy density is dropping. The universe is, very slowly, cooling as it expands. Not because heat is escaping somewhere, but because energy is being stretched across increasing space. Cold, in this sense, is not something that happens in places. It is something that happens in processes. Processes like expansion, processes like isolation, processes like radiation decoupling. This reframes the entire search for extreme cold. You do not look for emptiness. You look for situations where energy loses its ability to interact efficiently. And once you understand that, NAS, as work becomes more surprising, because if nature can create regions colder than the cosmic background using structure and expansion, then what happens when intelligence deliberately engineers those same conditions? What happens when you design isolation, when you control radiation exchange, when you force atoms into environments nature rarely allows? That is where the story stops being about cosmic accidents and starts being about deliberate creation of the coldest environments ever known. You assume nature always wins. Given enough time, enough scale, enough chaos, you expect the universe to reach every extreme on its own. Hotter than anything we can build, colder than anything we can imagine, more violent, more precise, more absolute. This is wrong. Nature is powerful, but nature is not always optimized for extremes. Nature balances competing processes. Radiation warms things while expansion cools them. Collisions add energy while emission removes it. Perfect isolation is rare. Perfect control is almost impossible. To reach the deepest cold ever measured, NASA did not search the sky. They built it not in Antarctica, not in deep ocean trenches, not even in space directly. They built it using atoms. Light and control so precise it feels unnatural. In laboratories, scientists use lasers not to heat atoms, but to slow them. This feels backward. You associate lasers with burning, cutting energy, but carefully tuned laser light can steal motion from atoms. Each photon collision removes a tiny amount of momentum. Over millions of interactions, atoms slow dramatically. Slower atoms mean lower temperature, but not in the simple way you imagine, not frozen solid, and not locked in place. Instead, atoms become easier to control, easier to trap, easier to isolate from outside energy. Then magnetic fields take over. Magnetic traps hold atoms in place without touching them. No physical contact, no thermal conduction. Just fields shaping where atoms can exist. Then comes evaporation cooling. The highest energy atoms are allowed to escape the trap. What remains is a population with lower average energy. Colder, more uniform, more synchronized. Layer by layer, randomness is removed. On Earth, gravity creates a problem. Even ultra-cold atoms fall. They hit trap boundaries, they interact. They gain energy, so NASA pushed further. They moved the experiment into orbit. In microgravity, atoms can float longer without falling into container walls. Without gravitational sag, without density gradients that reintroduce energy differences. In orbit, isolation improves. Control improves. Cooling goes deeper. Inside these orbital cold atom laboratories, temperatures have reached fractions of a billionth of a degree above absolute zero. Colder than most natural environments in the universe. Colder than interstellar gas. Colder than cosmic background structures. This is where your intuition struggles again, because you expect cold to look like frozen matter, solid, rigid, locked in place. Instead, ultra-cold atoms behave like something between matter and mathematics. They spread out, they overlap. They form shared quantum states that cannot be described by classical pictures of particles sitting in space. The colder it gets, the less atoms behave like tiny billiard balls. The more they behave like waves that forgot they were separate objects. NASA was not just measuring cold, they were creating conditions where classical reality stops being the dominant description of matter. And this reveals something uncomfortable. Extreme cold is not just about removing energy. It is about revealing deeper layers of how reality organizes itself when randomness fades. High temperature hides quantum behavior behind noise. Low temperature removes that noise, and what remains is not simple. Not empty, not dead. What remains is structure at a deeper level than your senses were designed to detect. And this leads to a harder break with intuition. Because once atoms are cooled enough, they stop acting like many things and start acting like one thing. Not metaphorically, not philosophically, physically. You think matter is made of pieces, tiny solid particles. Separate, independent, each one with its own position, its own motion, its own identity. Even if they are small, you imagine them as miniature versions of everyday objects, little spheres moving around, occasionally bumping into each other, but always remaining themselves. This is wrong. That picture only works when temperature is high enough for randomness to dominate. When atoms are warm, they behave like individuals because their motion constantly scrambles their relationships. Noise keeps them separate, but remove enough energy and separation stops being stable. Near absolute zero, something deeply uncomfortable begins to happen. Atoms stop behaving like individuals. They stop acting like a crowd. They begin acting like a single, shared quantum object. Not metaphorically, not visually, physically. This state is called a Bose-Einstein condensate, but the name is less important than what it means. At extremely low temperatures, the wavelengths associated with atoms, yes, atoms have wavelengths, become large enough to overlap. Normally, these quantum wavelengths are tiny compared to the distance between atoms. They never interact in a meaningful way. Each atom stays in its own quantum bubble, but as temperature drops, wavelengths stretch, random motion shrinks. The quantum description of each atom spreads outward. Eventually, those descriptions begin overlapping. And when enough atoms overlap in this way, the system can no longer be described as separate particles. The mathematics forces them into a shared state, one wave function, one collective behavior, one unified quantum object made from thousands or millions of atoms. Your intuition resists this, because you expect cold to freeze things in place. Instead, cold erases boundaries. In this state, if you disturb one part of the condensate, the whole thing responds, not through signals traveling from atom to atom, but because, in a real physical sense, they are not separate anymore. This is the point where everyday language begins to fail. You want to ask, where is each atom located? But the system does not have answers in the way you expect. The condensate exists as a shared probability distribution, a spread out presence, not a collection of points. And this is not science fiction. This is laboratory reality. Scientists have watched condensates flow without viscosity. They have watched them climb container walls. They have watched them interfere with themselves like light waves. Matter stops behaving like stuff. It starts behaving like pattern, even more unsettling. Identity becomes fuzzy. In a Bose-Einstein condensate, exchanging two atoms changes nothing. There is no meaningful way to label them. Individual identity loses physical meaning. This is deeply incompatible with how your brain models the world. You evolved to track objects, to distinguish one thing from another, to see boundaries as real and permanent. But near absolute zero, boundaries become optional, individuality becomes approximate, and this forces a deeper question about reality itself. If matter can stop being made of distinct things when energy becomes low enough, then what does that say about the idea that objects are fundamental? Maybe objects are not the deepest layer of reality. Maybe they are stable patterns that only appear when energy and randomness are high enough to keep things separated. When temperature falls far enough, reality stops looking like a collection of objects and starts looking like a unified field that temporarily allows object-like behavior. And this leads directly into an even more uncomfortable realization. Because if matter loses individuality at low energy, then what happens when you try to remove energy from empty space itself? You imagine empty space as nothing, no particles, no energy, no activity, just blank absence waiting to be filled. This is wrong. Even if you remove every particle, even if you block every photon, even if you cool a region as far as physics allows, something remains, not because technology is imperfect, not because measurement disturbs the system, because reality itself does not permit perfect emptiness. At extremely low temperatures, experiments begin to reveal a strange flaw. A lowest possible background activity that cannot be removed. This is not leftover heat. It is not contamination. It is built into the structure of quantum physics itself. This is called zero-point energy. Your intuition says zero energy should mean zero motion. Perfect stillness, absolute silence. But quantum mechanics does not allow both perfect stillness and perfect certainty of position. The uncertainty principle forces a minimum level of fluctuation. Even in the lowest possible energy state, particles cannot sit perfectly still. Fields cannot be perfectly flat. Tiny fluctuations must exist, not sometimes, always. This means that even empty space is not truly empty. It is filled with quantum fields that never fully stop moving. Tiny energy variations appear and disappear constantly. Not because something is causing them, because the rules of reality require them. These are called vacuum fluctuations. At normal temperatures, this background activity is invisible compared to the chaos of thermal motion. But as systems get colder and colder, thermal noise fades, and this deeper layer becomes detectable. Experiments have measured forces caused purely by vacuum fluctuations. In certain conditions, two metal plates placed extremely close together will experience a tiny attraction, not from gravity, not from electromagnetism in the normal sense, from differences in allowed vacuum fluctuations between them. This is deeply disturbing to classical intuition because it means nothing can push on things. It also means cooling a system is not like draining water from a tank. There is no final empty state waiting at the bottom. There is only a lowest allowed energy pattern, a minimum level of unavoidable activity, even more uncomfortable. This vacuum energy exists everywhere. It is not something located inside matter. It is part of space itself. So when NASA or any laboratory cools atoms close to absolute zero, they are not approaching nothingness. They are approaching the lowest possible interaction with these underlying quantum fields. You can reduce thermal motion. You can reduce random collisions. You can isolate systems from external radiation. But you cannot remove the quantum structure of space itself. This changes the meaning of cold again. Cold is not the path toward nothing. Cold is the path toward the deepest layer of something. At high temperatures, reality looks like objects interacting through forces. At ultra-low temperatures, reality starts to look like fields fluctuating underneath everything, constantly, quietly, permanently. And this leads to the final, unavoidable limit. Because if zero-point energy cannot be removed, if uncertainty cannot be eliminated, then maybe absolute zero is not just difficult to reach. Maybe it is fundamentally unreachable. You imagine absolute zero as a destination, a final step, a last decimal place, a point you could reach if you just removed the last trace of energy. You imagine it like stopping a clock, like freezing a frame, like pressing pause on reality itself. This is wrong. Absolute zero is not a location you can arrive at. It is a boundary condition, a limit that physics allows you to approach but never touch. This is not a technological problem, not a matter of better machines or more precise experiments. It is written into the rules that govern energy, entropy, and information. The third law of thermodynamics states that as temperature approaches absolute zero, removing additional energy becomes harder and harder. Not linearly harder, not gradually harder, infinitely harder. Each step towards zero requires exponentially more control, exponentially more time, exponentially more precision. You can always get closer, but the final step requires removing the last possible energy fluctuation. And physics does not give you a mechanism to do that, because removing energy requires interaction. You must let energy leave a system through radiation or collisions or coupling to another system. But every interaction introduces uncertainty. Every interaction introduces disturbance. To remove the last unit of energy, you would need perfect isolation and perfect extraction simultaneously. Physics does not allow both at once, and then quantum mechanics adds another wall. If you try to pin a particle perfectly still, you must know both its position and momentum exactly. But uncertainty prevents that. The more precisely you lock position, the more uncertain momentum becomes. The more you constrain momentum, the more position spreads out. Absolute zero would require perfect certainty in both. Reality refuses. Even theoretically, the ground state of a system, its lowest possible energy configuration, still contains zero-point motion. The system is not dead, not silent, just quieter than anything classical physics would predict. And the closer you get to that ground state, the more fragile the system becomes. External radiation, cosmic rays, magnetic noise, gravitational fluctuations, even measurement itself can inject energy back into the system. The universe is not built for perfect stillness. There is also a deeper, stranger consequence. Temperature is tied to entropy, the number of possible microscopic configurations a system can have. At absolute zero, entropy would reach its minimum possible value, a perfectly ordered state, only one allowed configuration. But reaching that state would require removing all uncertainty about the system's microscopic structure. That is not just difficult. It may conflict with the fundamental probabilistic nature of quantum mechanics itself. So absolute zero becomes less like a physical temperature and more like a mathematical edge, a direction you can move toward forever without arriving. And this changes how you should think about reality. You were taught that physics is about finding ultimate values. The coldest temperature, the smallest distance, the shortest time, the final layer, but many of physics' deepest limits are not points. They are asymptotes, boundaries you can approach endlessly, revealing more structure, more subtlety, more hidden behavior. without ever reaching a final, frozen state. This is where the story stops being about cold, because the coldest experiments ever performed are not demonstrations of emptiness. They are demonstrations that the universe has a lowest layer of activity that cannot be turned off. Reality is not something that can be paused, not completely, not perfectly, not ever. Even at the coldest temperature you could ever measure, something would still be fluctuating. Some field would still be vibrating. Some probability would still be spreading through space. The universe does not allow perfect nothingness. It does not allow perfect stillness. It allows only deeper and deeper levels of quiet structure. And that is the part that should disturb you. Because it means reality is not built on objects sitting in empty space. It is built on something that never fully stops moving, even when everything looks frozen. And the deeper you go into cold, the more the universe stops looking like matter and starts looking like possibility. Not possibility in the sense of imagination, possibility in the sense of what is physically allowed to exist. Absolute zero is not the death of reality. It is the horizon where reality becomes pure structure, pure law, pure potential, and you can approach that horizon forever, but you will never cross it